This question says, the conductivity of sodium chloride at 298 Kelvin has been determined at different concentrations and the results are given below. Fine. You have concentration in terms of moles per liter and you have kappa in Siemens per meter, but it's not just kappa, it is kappa multiplied by 100. So that the value looks good. Fine. This is the thing. Calculate lambda m for all concentrations and draw a plot between lambda m and root c. Find the value of lambda m naught. How do we do this? Let's begin. How do we begin? Well, let's recall the formula. Lambda m, molar conductance, is kappa into 10 raised to minus 3 by c. If the units are SI units or meter. Please remember, in case CGS system is used, we use 10 raised to minus, instead of 10 raised to minus 3, the formula shows 10 raised to plus 3. But nonetheless, we have meters and Simon per meter if you notice this. SI units, so we are using 10 raised to minus 3 in the formula. So using that, can I find lambda m for various concentrations? Yes. And I'm supposed to plot lambda m versus root c. Okay. So I would prepare one more table along with, like I'm already given a table, right? So along with, in parallel, I would need one more table calculating lambda m and root c. So kappa has to be multiplied by 10 to minus 3. So we already have 100 times kappa as this. Let's start. We'll substitute and calculate. So lambda m for the first case, how much would be lambda m? Lambda m is kappa, which is 1.237 into 10 raised to minus 3. Now, this is 100 kappa. So kappa actually this much into 10 raised to minus 2. 100 times kappa is 1.237. So kappa itself would be equal to 1.237 into 10 raised to minus 2. That multiplied by 10 raised to minus 3, oh my god, that is even worse. Divided by what? Concentration, which is 10 raised to minus 3. That wanes off. So I get kappa as 0.01237 Simon meter square per mole. And actually this is not the value of kappa. Kappa only this much. What we have calculated here is value of lambda m, which is how much? Kappa, this much is kappa multiplied by 10 to minus 3 upon c, and it is so much. Is it the first value? Yes. What about second, third, fourth? Well, win over each of them one by one. We have this now, we have to multiply it by 10 to minus 5. So once we take this value, now we don't have much space here. Can I do this up so that we have more space for the third entity? Fine. So that would be 11.85 into 10 raised to minus 5. Why minus 5? 10 raised to minus 2 from here and minus 3 from the formula, so that would make it 10 raised to minus 5 again. Divided by concentration. Concentration is 10 raised to minus 2. How much would that be? That is 11.85 into 10 raised to minus 3. Okay, and how much is that? 1, 2, 3. This is 12.37. This is 12.37 into 10 raised to minus 3. Units are same, Simon centimeter square per mole. This much. The third one, let's see what do we get? 23.15. 23.15 divided by 2 into 10 raised to minus 2. And this is 10 raised to minus 5. How much is this? Let's divide. This is 11 point, how much? 5, fine, and 15 to 7, 5 into 10 raised to minus 3. From 12.3, 11.8, 11.575, it seems to be reducing. The next one and the next one. It's a very routine calculation. So this is 55.53 into 10 raised to minus 5 divided by 0.05. Fine, that is 11.106 into 10 raised to minus 3. And the last one, 106.74 into 10 raised to minus 5 divided by 0.1. Oh my god, how much is that? That is sorry, this is 10.674 into 10 raised to minus 3. Units are same, Simon meter square per mole. These are the different values of lambda. In experiments 1, 2, 3, 4, 5, this is what we have calculated. And the instruction is plot them against root C. It's not just C. We are supposed to take a dirty square root of C. Let's do that. How much is root C? Let's see. Root C would be, if I take a square root of this, for convenience, let me take this as 10 into 10 raised to minus 4. So what I get is root 10 into 10 raised to minus 4. Root 10 is 3.16. So I have 3.16 into 10 raised to minus 2 molar to the power half. This is root C here. What about root C here? 0.01 10 raised to minus 2. This is 10 raised to minus 1. 100 into 10 raised to minus, sorry. This is simply 10 raised to minus 1, which is 10 into 10 raised to minus 2. This is root C. What about this? This is 20 into 10 raised to minus 2. So, no, 2 into 10, this is 2 into 10 raised to minus 2. If I take a square root, 1.414 into 10 raised to minus 1. This is root of 5, 2.23. Into 10 raised to minus 1. How much is that? Root of 10 into, this is 3.16 into 10 raised to minus 1. What I'm taking, I'm just doing root C, that's it. And this is very ugly. So I'll also convert this to 0.316, like this. So this is simply 10 raised to minus 1. 1 into 10 raised to minus 1. So 10 raised to minus 1 is common throughout. 0.316, 1, 1.414, 2.23 and 3.16. Root C is consistently increasing and we can see lambda m is consistently decreasing. So what do I get? I get, of course, if I plot lambda m versus root C, I would get a straight line going down. If I extrapolate this line, if I extend this line ting here, then at this point, I get lambda m naught. That would be the value of lambda m naught, right? So one portion we have done, we have calculated all the lambda m's, root C, we have all data points, and the next step lies in actually plotting a proper graph. Let's do that. Now students, if you take a look at this, we have to plot lambda m versus root C. I'm going to use this opportunity to tell you some very beautiful facts about graph plotting also. It is not just this question. I'll be telling you in general a lot many ideas about how exactly to plot a good graph. Graph anybody can plot, but there are few points. Say for example, lambda m versus root C. Look at the values of lambda m. You have 12.37, 11.85, 11.58, 11.11, 10.67. So from 10.67 you get 11.37. There is some kind of a variation, but then the variation in data is in a very narrow range, between 2 units. From 10.67, if I add 2 also, I get 12.67 and the maximum value is 12.37, which is lesser only. If I just start the origin from 0, I would get a very flat graph or a very small kind of a line. A good graph is that which uses the entire graph paper. So please note, your origin need not start from 0. On y-axis, if I say I choose to start from, instead of 10.6, since the beginning point is 10.67, I could begin with 10.5. Oh wow, you're beginning with 10.5, why not 0? I could use 0, my dear, but if I use 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Say for example, I use, so 10 would be here and 12 would be here. So entire graph would be finished between this strip. This portion of my graph paper is a waste, this portion of my graph paper is a waste. So what is my aim? My aim is only to utilize my graph paper? No. The aim is to reduce error. The more expanded version of graph I make, the less is going to be the error, as you will see very shortly. So yes, we could use origin as 0, 0, but this is not the best thing in this case. I'm starting the origin from 10.5 for y-axis. For x-axis, 0.3 to 1, 1.41 to 3. We could start with 0 also, because 0.3, 2 and 1 such values are there. And how many spaces? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 centimeters. Now, if I just plot this till say this around 4, so then 1, 2, 3, 4. If I take this as 1, 1, 2, 3, 4, this as 2, 1, 2, 3, 4, this as 3, and 1, 2, 3, 4, this much as 4. Please note, I could have taken 1, 2, 3, 4 centimeters also like this. In that case, all I would have got is a very stupid graph like this. That's it. A simple ting, 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 4 points clustered together, and the rest of the graph paper is blank. You understand nothing. So I have used a scale in which I can utilize the entire paper, and I can spread this over. Are you getting that? In the same fashion, when you look at lambda m, which scale I'm trying to use? From 10.5, I have intentions to go till 12.5. And this is, up till here, this is 20 centimeters. So if this is 20, to 10.5, I'll say this is 11.5, and I'll say this is 12.5. Oh my God. So I'm using the entire spectrum. So what is the scale? In this case, from 10.5 till 11.5, I'm just covering 1 unit. So 1 centimeter, there are 10 centimeters is 1 unit change. That means 1 centimeter on y-axis, 1 centimeter corresponds to how much? 0.1 into this 0.1 units. What are the units? These are 0.1. For 0.1 variation in lambda m, I'm going to use 1 centimeter. Beautiful. And for root C, as you can see, I'm using 4 centimeters for 1 unit. So 4 centimeters, 1 centimeter corresponds to 4 units. No, sorry, 4 centimeters correspond to 1 unit. Sorry for this ugly mess, but then this is the way it is. 4 centimeters. If you're confused, look here. I'm using 1, 2, 3, 4 centimeters, and this is only 1. So 1 unit of root C, I'm using 4 centimeters. Is that fine? Let us begin to plot. So 0.32. First, 1 looks good. I'll plot 1. So lambda m is 11.85. Now 11.5 is already here. Fine, I'm using pencil now. 11.5 is here. Then this would be 11.6, 11.7, 11.8. 11.85. Beautiful. I have this point. 11.85. Let me just to highlight that. Let me use ink. I have located this. What did I do? See, every centimeter corresponded to 0.1 units. So 11.5, this is 11.5. 1 centimeter, 11.6. 1 more centimeter, 11.7. 1 more centimeter, 11.8. And then half a centimeter, 11.85. Very accurate. And that gives me the ability to plot decimals also very beautifully like this. I have plotted 1 point. Congratulations. What about 0.32? Now, since 1 unit is 4 centimeter, 0.32 units is 0.32 multiplied by 4. And how much would that be? 1.28. 1.28 centimeters. So 1.28 or 1.3 centimeters. So find 1.123 centimeters. I have got this. And how much up? This is 12.37. Lovely. Now 12.37. This is 11.5. Fine. Then 0.6, 0.7, 0.8, 0.9, 12. So this is 12. Yes. Then 12.1, 12.2, 12.3. Yes. And 7 up. The 12.37. I'm getting this line. This line is on this horizontal, I have 12.37, and on 1.3 centimeters. So I'll just take 1.3 centimeters here. 1, observe very carefully, 1.3 centimeters. 1, 2, 3. This is the point. So 1.3 from x-axis, on the x-axis, and so much distance on y-axis. Yeah, very beautifully, this is my point. So I've got this point, I've got this one. Similarly, let us plot the remaining ones also. Similarly, let us draw the remaining 3 points also, which I've got marked. And they, as you plot them, you might be horrified to discover that they don't really appear to be in a straight line. Oh, we have made an error. No, not really. See, we have plotted the experimental values. And now comes a very, very important point. You are supposed to draw a straight line through these points. Now, this might sound perfectly absurd. How can you draw a straight line when there is no straight line? This looks like a curve. And again, it looks like another curve. Now, when such a case is there, please understand we are supposed to get a straight line. So what will we do? We try to make a straight line which passes through as many points as possible in such a way that if you draw a line, a straight line, then if it doesn't pass through all the points, then the points which don't fall on it, half of them should be on one side and the other half should be on the other side. The deviation, the average deviation on this side and that side should be the same. So what do you mean we don't understand? See, it's like this. I'll just give you an example. Now see, for example, if I draw a straight line passing through these points. Now, is this a good drawing? No. Why? Because I will be getting 2 points exactly on one side of the line and no points would be on the other side. There are just 5 points. If I take these 3 roughly on my line, then this is not a good idea. Can I take, say, for example, if I take these 3, is this a good idea? This looks like a much better idea. Why? Because I've got 1 point on this side and just note 1 point on the inside and outside. Well, so shall I draw the line? Yes, definitely. Let me. I'll need to rotate this so that at least I can see this and draw the line for you. And as we do this, can you see that there is 1 point and the other point on 2 sides, and roughly the distance between them and them, this side and that side, is approximately the same. You could say that maybe if somebody else draws this, the person would have drawn a slightly different line. Yeah, very much possible. It could be very drastic also. Say, for example, if you draw something like this, this would look like, these 3 points also are more or less collinear. If you draw a line like this, you get a very different slope. But then this is wrong. Why? Because the remaining 4 and 5, they are both on the same side, which indicates that this is not a good fit. So, whenever you are trying to fit a line in between, say, 5, 6, 7 points which are not collinear, please remember that line is considered more accurate, which is drawn in such a way that some points lie on one side while the other points lie on the other side. The perpendicular distances also should be roughly the same. So in this case, I guess we have a very good fit. Does this question possess a unique answer? No. Why? Because slight variation in the exact answer may be there depending upon which line one chooses to make or fit. But now that we have it, can we see where exactly this graph is touching y-axis? Because at whichever place that y-axis is being touched, I get lambda naught m or molar conductance at infinite dilution. If you read this value, this comes out to be lambda naught m is 12.39 into 10 is to minus 3 are the units which we have talked about. So for lambda naught m, this is the graph and that is the answers